Are you a computer science student struggling with Python fundamentals? This complete tutorial covers everything from your first Hello World program to understanding how computers actually process your code. I'll walk you through Python syntax, debugging techniques, IDEs like Visual Studio Code, and even dive into computer architecture basics. Whether you're prepping for exams, tackling coding assignments, or building your programming foundation, this video has everything you need to succeed. Let's get started. Getting Started with Python Programming by the Programming Professor. Let's begin with an overview of what this presentation covers. First, we'll explore how programming applies to the technology we use every day. Then we'll introduce Python itself and how the interpreter allows us to run Python code interactively. After that, we'll walk through writing Python programs in a file and running them from start to finish. We'll look closely at basic input and output, how programs display information and receive data from the user. We'll also dive into common programming errors, how to recognize them, and most importantly, how to fix them. We'll take a look at development environments that make coding easier, and then we'll go under the hood to see how computers really run our programs. Finally, we'll wrap up with a brief but interesting history of Python and why it's become such a dominant force in the programming world. So what exactly is a computer program? Think of it as a series of instructions that a computer follows, one step at a time. Programs power everything from the apps on your smartphone, to online services like Netflix and Amazon, to navigation systems in cars and autopilot in airplanes. There are three fundamental types of instructions: input, process, and output. Input is how the program gets information. This could come from a file, the keyboard, a touchscreen, or even the internet. Then there's processing, where the program does something with that data, like calculating a total or making a decision. Finally, output is the result. This could be something printed to the screen, saved in a file, or sent across a network. Programs use variables, like x, y, and z, to store values that can change as the program runs. The term variable actually comes from this ability to vary. If you've ever used a calculator or spreadsheet, you've already worked with variables in some form. Here's a great analogy to help make programming more intuitive. Think of a program like a cooking recipe. A recipe is a sequence of instructions. Mix this, add that, bake for 8 minutes at 350 degrees. Each step must be followed in order to get the correct result. Similarly, a computer program is a set of instructions that the computer follows, like reading input, performing calculations, and displaying results. Let's use baking chocolate chip cookies as an example. You might start by mixing butter and sugar, adding an egg, stirring in flour and chocolate, and then baking. A computer program might start by receiving two numbers, adding them together, and printing the result. Both processes follow ordered, logical steps. The big difference: the computer will follow your instructions exactly, even if they're wrong. So just like with recipes, precision matters. Let's apply this concept with a hands-on programming activity. Imagine you have a variable named m. Your task is to perform a series of instructions that update its value and print the result. In this example, m starts at 5, then gets doubled, squared, and increased again. You can change the order of these steps, and you'll see different results. That's because in programming, the order of instructions dramatically affects the outcome. This is what we mean when we say a program's state changes step by step. It's like a recipe where mixing the ingredients before turning on the oven gives you cookies, but flipping those steps could result in a disaster. The key takeaway here is this: in programming, order matters. One misplaced instruction can completely change what your program does, or whether it works at all. Now, let's go deeper into that programming activity we just introduced. On this slide, we can actually see what the program does, step by step. It begins with m equals 5, then prints the value, multiplies it by 2, prints again, squares it, prints once more, and finally adds 15 and prints the result one last time. What's really cool is that if you rearrange these instructions, say, if you add 15 before squaring or print before updating, the output completely changes. This activity demonstrates a core truth in programming: execution is sequential. The computer performs one instruction at a time, and each instruction builds on the result of the last. So just like stacking blocks, if you build out of order, your program will collapse or give incorrect results. This is a simple but powerful way to learn the impact of instruction order and how code flows. Think about changing the order. Can we make the output greater than 500? How about 1000? Now that we've seen how instruction order changes program behavior, let's step back and talk about a bigger idea: computational thinking. This is more than just coding, it's a way of approaching problems. In the industrial age, mathematical thinking was essential. Today, in the information age, computational thinking is just as important. So what is it? It's the ability to break down problems into smaller parts, devise a step-by-step plan to solve them, and think logically and systematically, like a computer would. This mindset is helpful not only for writing programs, but also for solving real-world problems. Think about following a recipe, building IKEA furniture, or debugging why your Wi-Fi isn't working. All of those require structured thinking. And in programming, that structure is formalized into something we call an algorithm, a precise sequence of steps to solve a problem. The best part: you don't need to be a professional programmer to benefit from computational thinking. It's a skill for life. So, how do we actually write and run code? That's where the Python interpreter comes in. Think of the interpreter as a program that runs other programs, specifically Python code. When you're using the interactive interpreter, it waits for you to type one line of Python at a time, and then immediately executes it. You'll know it's ready because it shows a prompt, the triple greater than symbol. For beginners, this is a great way to test ideas or explore how Python works. In fact, early on, you can use it like a powerful calculator. You can assign values to variables, perform math operations, and print results instantly. In the example shown here, we assign a value of 20 to the variable wage, then 40 to hours, calculate the total wage, and print the result. The interpreter responds with the output, 800. It's fast, interactive, and ideal for learning. Now, while the interactive interpreter is useful for trying things out, it's not great for writing full programs. That's where creating Python files comes in. Instead of typing one line at a time, you write a full program in a .py file and run it all at once. The Python interpreter reads the file line by line, from top to bottom, executing each instruction in order. In the example shown here, we're calculating a weekly salary. The program starts with a comment to describe what it does. Then we define the wage and hours variables, multiply them, and print the result. This introduces a few important programming concepts. A statement is any instruction the interpreter executes, like assigning a variable. An expression is something that produces a value, like wage times hours. The equal sign is used to assign values. Print is used to display output. And the hash symbol is used for comments. These don't affect the program's behavior, but they help humans understand the code. It's a simple but complete Python program. So now that we know how to write and run a program, let's look at how we control what it outputs. The simplest way to produce output in Python is using the built-in print function. This function sends text to the screen, usually for the user to see. To print text, we use quotes to create a string. A string is just a sequence of characters, letters, numbers, punctuation, spaces, and even special symbols like @ or hash. For example, the line print, "Hello World," will display that exact message on the screen. Similarly, you could print an email address or even a hashtag. Strings are one of the most basic but powerful tools in programming. We use them to represent everything from labels and messages to usernames and file names. The key takeaway here: if it's meant to be shown as literal text, put it in quotes and print it using the print function. In the last slide, we saw how to print basic text using Python. Now, let's take it a step further and print dynamic content, values stored in variables. Instead of hard-coding the output, you can have Python display the current value of a variable. You do this by passing the variable name to print without quotes. For example, if we've assigned wage equals 400, then using print, your daily wage is $wage will output. Your daily wage is $400. Notice that we're separating the string and the variable using a comma. That tells Python to print both, with a space in between. It's smart enough to automatically format this. You can even print multiple values in one line, such as printing both the daily and weekly wage, and Python will neatly space everything out. This flexibility allows your program to respond to changes in variable values. For instance, if wage changes, the printout will reflect the new amount. This is a key part of what makes programming dynamic and interactive. By default, Python's print function adds a new line after each line of output. That means if you call print 3 times, you get 3 separate lines. But sometimes, we want to keep printing on the same line. That's where the end parameter comes in. You can add end equals to a print statement to keep the next output on the same line with a space after it. This is super useful when you want to format a sentence over multiple print calls. In the example here, we print hello there. Then my name is, and finally Carl. But by using end equals, each time the output stays on the same line. You can change the separator too. For example, use a dash or no space at all. This gives you greater control over how your program's output is formatted, which becomes especially important when you start building user-facing applications or working with formatted data. Just as you can keep output on the same line, you can also control when to break lines manually. That's where escape sequences come in, and one of the most common ones is \n, which represents a new line. So when you write print 1\n, 2\n, 3, Python outputs each number on its own line. Escape sequences always begin with a \, and they tell Python to insert something special. A few other common ones include \t for a tab, great for lining things up in columns, and \/ for printing a literal \. These sequences might look strange at first, but they're essential when you want to format your output neatly. In the example here, the program uses tabs and new lines to print a table-like display with names and jobs, clearly structured for the user to read. This also introduces the concept of white space, spaces, tabs, and new lines, which play a big role in how output is interpreted and validated, especially in automated testing or grading environments. Now that we know how to output information, let's learn how to take input from the user. This is where your programs become interactive. Python uses the input function to read user input from the keyboard. When you call input, your program pauses and waits for the user to type something and press enter. That value is returned as a string, even if the user types a number. You can store the result in a variable for later use. In this example, we prompt the user to enter the name of their best friend, store it in the variable best friend, and then print it out. This simple interaction makes your program feel alive. You can now build programs that respond to the user, instead of just displaying hard-coded results. One thing to remember: input always comes in as a string. So if you're planning to do math with it, you'll need to convert it, which we'll cover in the next slide. All input in Python is initially stored as a string. That means it's treated like text, even if it looks like a number. So when a user enters 123, it's actually the string 123, not the number 123. This distinction is important because types determine how values behave. You can't divide a string by a number, or add a string to an integer without converting one of them first. If you try to perform math on a string without converting it, Python will raise an error. To handle this, Python provides the int function, which converts a numeric string into an integer. In the example here, the program prompts the user to enter a number, stores it as a string, then converts it to an integer using int. Once converted, we can do math with it, like doubling it, and display the result. This introduces the important concept of type conversion, and also reminds us that user input must be carefully handled before it can be used in calculations. We just learned how to get input from the user and convert it into a number using int. But there's actually a slightly cleaner and more intuitive way to prompt the user, and that's by placing your message directly inside the input function. Instead of using a separate print statement to ask a question, you can write something like input, enter your name, and the prompt appears right where the user is expected to type. This not only saves a line of code, but also makes the interaction feel smoother. In the example shown here, we ask the user for their best friend's name in one concise line. It's easier to read and just as functional. As your programs grow, small improvements like this in formatting and clarity can make a big difference in code readability and user experience. Now let's talk about something every programmer encounters: syntax errors. These are mistakes that break the rules of the Python language. The interpreter catches these errors before the program runs, and it won't execute anything until you fix them. Common syntax mistakes include things like missing parentheses, forgetting quotation marks, or trying to put two print functions on the same line without separating them properly. In the example here, Python throws a syntax error because two print calls are placed side by side on the same line, which it can't understand. Python helpfully tells us which line has the problem, though the message might seem a bit cryptic at first. As you gain experience, you'll learn to quickly interpret these messages and fix the issue. Just remember, syntax errors are usually easy to resolve once you find the offending line and understand what Python was expecting. So how do we avoid getting overwhelmed by all these errors? That brings us to a great piece of advice: write your code in small, testable chunks. New programmers often try to write a full program all at once, only to run it and be faced with a wall of errors. That's super frustrating and unnecessary. A better practice is to write 3 to 5 lines of code, then run it, test it, and fix any problems. Once those lines are working, write a few more and repeat the process. This approach helps isolate issues and gives you the confidence that what you've written so far is solid. Experienced developers do the same, they just get better at predicting what will work. The key is frequency. Run your code early and often. This reduces debugging time, helps you understand error messages in context, and builds your skills gradually without getting overwhelmed. Now let's look at a different kind of error, one that happens after the program has started running. These are called runtime errors. A runtime error occurs when your code is syntactically correct, meaning it doesn't break any rules, but it tries to do something impossible. For example, dividing by 0 or converting the word hello into an integer using int. In this example, the program runs smoothly at first, calculating and printing a salary. But when the user is prompted to enter a number and types the word Henry instead, Python crashes with a value error. Why? Because the int function can't convert letters into a number. The interpreter stops immediately and displays a traceback, which is Python's way of telling you what went wrong and where. Runtime errors are common, and they often come from unexpected input or unhandled edge cases. As you write more code, you'll get better at anticipating them, and eventually, you'll learn to handle them gracefully using error handling techniques. Speaking of errors, Python doesn't just throw errors randomly. It actually classifies them into types, which can help you understand what's going wrong. Let's take a quick tour through the most common types you'll see. A syntax error means your code violates the rules of Python, like forgetting a colon or using invalid syntax. An indentation error occurs when your code isn't properly aligned. Remember, indentation matters in Python. A value error, like we just saw, means you passed an inappropriate value to a function, like trying to convert text into a number. A name error means you used a variable before defining it, maybe a typo, or you forgot to assign it. And finally, a type error occurs when you try to mix types that don't go together, like adding a number and a string. These error types are Python's way of guiding you toward the problem. If you pay attention to the error messages and understand what they mean, you'll fix bugs faster and become a better problem solver. So far, we've talked about syntax errors, which stop your program before it runs, and runtime errors, which crash at mid-execution. But there's a third kind of error that's even sneakier: logic errors. A logic error happens when your code runs just fine and doesn't crash, but the result is wrong. And that makes it hard to catch, because the computer thinks it did everything right. The problem is in the logic, the way the instructions were coded. For example, say you meant to multiply 2 by 40, but you accidentally wrote 2 times 4. The program won't complain. It will just give you an answer, in this case, 8, which is technically correct from the computer's perspective, but totally wrong from yours. These errors are often called bugs and can be the most frustrating to track down. They usually come from typos, incorrect formulas, or assumptions you made in your code. Debugging logic errors requires careful testing and comparing your actual results to what you expected. The best strategy: think like a detective, retrace the logic step by step. Now that we've covered how programs can go wrong, let's talk about where you actually write and run your programs. This is where IDEs come in. IDE stands for Integrated Development Environment, and it's like a one-stop shop for all your coding needs. Instead of jumping between a text editor, a terminal, and maybe a debugger, an IDE brings all those tools together into a single application. You can write code, run it, debug it, organize your files, and even control version history, all in one place. Popular Python IDEs include IDLE, which comes with Python, as well as more advanced options like Visual Studio Code, PyCharm, and Xcode. Some IDEs are installed locally on your computer, while others run in your web browser using the cloud. Either way, the goal is the same: make programming smoother, faster, and more manageable, especially as your projects grow. If you're just getting started, IDLE or Visual Studio Code are great places to begin. Let's take a closer look at what makes IDEs so helpful. First, there's syntax highlighting. Your code is automatically colored so that keywords, strings, and variables are easy to tell apart. This makes it easier to read your code and also spot errors, like missing quotation marks or mismatched parentheses. Next is automatic delimiter completion. When you type an opening parenthesis or quotation mark, the IDE adds the closing one for you. This prevents a whole class of bugs before they even happen. IDEs also have shortcut buttons that let you run or debug your code with a single click. No need to type commands every time. And let's not forget the File Manager and Editor tabs, which help you navigate between different parts of your project quickly and stay organized. These features might seem small, but they save you time and reduce errors, which is a big deal when you're learning or working on complex projects. One especially important part of an IDE, or any development workflow, is the console. This is where your program's input and output appear. If you use the input or print functions, the console is where the user types responses and sees results. But behind the console is something even more powerful, the command line interface, or CLI. The CLI is a text-based tool that lets you run programs, manage files, and issue commands directly to your computer. It's a bit like talking to your operating system without using a mouse or clicking windows. One of the best features of a CLI is support for command line arguments, values that you provide when you start a program. For example, in the command ls-a, ls is the program, and dash is an argument that tells it to show hidden files. Similarly, you could run a Python program and pass in values it uses, like settings, file names, or options, directly from the command line. Once you get comfortable with it, the CLI becomes an incredibly efficient way to interact with your code. Now let's go a level deeper into how computers actually work under the hood. Understanding this helps you appreciate why programming requires such precision. Let's start with the switch, one of the most basic elements of computing. Back in the 1800s, switches were used to control electrical circuits for lights and machines. Then, in the early 1900s, engineers developed electronically controlled switches, which could be flipped on and off automatically, not just manually. A high voltage represented the number 1, and 0 voltage represented 0. These two states, 1 and 0, are known as bits, short for binary digits. Everything a computer does is built from these bits. By connecting thousands, or even billions, of these switches together, engineers created circuits that could perform logic operations and calculations. In other words, the foundation of modern computing is a massive network of on-off switches. And just like ingredients in a recipe, the way these switches are connected determines what the computer can do. Now that we've introduced switches and the concept of bits, let's talk about how these pieces evolved into something as powerful as a modern processor. Back in the 1930s and 1940s, the first electronic computers were massive. They filled entire rooms and used over 10,000 switches. Despite their size, these machines could only perform a few thousand calculations per second. That might sound slow today, but at the time it was groundbreaking. These early computers were mainly used for complex scientific and military calculations, like computing ballistic trajectories. But soon, engineers realized they could build more flexible machines by allowing them to execute different instructions. This led to the creation of processors, circuits that could follow a sequence of commands stored in memory. Originally, those instructions were configured using physical switches, a very manual process. Today, though, processors are tiny. They fit on a chip the size of a postage stamp, and instead of thousands of switches, they contain billions. These chips can process data at incredible speeds, enabling the powerful computers we now carry in our pockets. So how does a computer actually execute a program? It comes down to two parts, the processor and the memory. Memory is like the computer's short-term storage. It holds instructions, the steps that make up a program, and the data those steps work on. Think of memory as a long list of numbered boxes, each capable of holding a value of 0 or 1. The processor reads instructions from these boxes one at a time, performs calculations or actions, and may store the results back in memory. Here's a helpful analogy. Imagine the processor is a chef, the memory is the kitchen counter, the recipe is the program, and the ingredients are the data. The chef follows the recipe step by step, using ingredients and placing things back on the counter as needed. This constant back and forth between processor and memory is how all software runs, from calculators and games to web browsers and video editors. It's simple in principle, but powerful in practice. Now let's take a look at what kinds of instructions a processor can actually execute. At the hardware level, computers don't understand Python or JavaScript. They only understand very basic commands like add two numbers or store a value. These are called machine instructions, and they operate on specific memory locations. In this slide, we're introduced to 5 common instruction formats: add, sub, mul, div, and jmp. For example, add x num y means take the value at memory location x, add a number to it, and store the result at location y. The same goes for sub, mul, and div, which perform subtraction, multiplication, and division. Then there's jmp, short for jump, which tells the processor to go to a different part of the program. This is essential for making loops and conditional logic. These low-level instructions form the building blocks for everything your code does, even if you're writing in a high-level language like Python. To understand how powerful these instructions can be, let's look at a specific example. Suppose we have the instruction mul 97, 9, 98. This means multiply the value at memory location 97 by 9 and store the result in memory location 98. If memory 97 holds the value 20, then memory 98 will end up with 180. That's a simple multiplication, but here's where it gets interesting. Under the hood, this instruction is represented in binary, zeros, and ones. The machine code version of this might look like a long sequence of ones and zeros, where each segment encodes the operation type and the memory addresses. At this level, the processor doesn't know it's doing a multiplication. It just sees a string of binary values and performs whatever operation is mapped to that sequence. When we write high-level code like f equals 9 times c, divided by 5 plus 32, the compiler or interpreter breaks it down into dozens of these low-level instructions. So even a seemingly simple line of Python turns into a complex series of hardware-level operations that the processor executes lightning fast. Writing machine instructions manually, like in the previous slide, is not only tedious, it's also incredibly difficult to manage for anything beyond the simplest programs. That's why modern programming evolved in stages. In the 1940s, programmers wrote each instruction directly in binary, strings of zeros and ones, which we now call machine code. But as computers got more capable, it became clear that humans needed a more readable way to code. That led to assembly language, where instructions like mul 97, 9, 98 replaced raw binary with something easier to understand. Assemblers were then used to translate this readable code into machine instructions. But even assembly was still quite low level. In the 1960s and 1970s, we saw the rise of high-level languages like Fortran and Algol. These allowed programmers to write code in math-like syntax. For example, f equals 9 divided by 5 times c plus 32. High-level languages are much closer to how humans think, and compilers were created to translate this high-level code into low-level machine instructions. This evolution is what makes modern programming possible. We write code in an expressive, abstract way, and let the computer do the heavy lifting of translating it into instructions the hardware understands. Let's wrap up our under the hood tour of the computer by looking at its major components. A modern computer is made up of several interconnected parts, each doing a specific job. First, we have the input and output devices, or I/O. These include things like your keyboard, mouse, touchscreen, microphone, speakers, USB ports, and of course, the screen or monitor. These peripherals allow you to interact with the computer, whether you're giving it data or receiving feedback. Next is storage, which is typically a solid-state drive or SSD. This is where all your files live: programs, documents, videos, even your operating system. SSDs use flash memory, meaning they can retain data even when the computer is turned off, and they're much faster than the old spinning hard drives they replaced. Then we have memory, or RAM, which is your computer's short-term memory. It stores the data your system needs right now and clears it when you power off. RAM is fast but temporary. At the heart of everything is the processor, or CPU. It executes instructions and controls nearly every other component. Finally, there's the clock, a tiny, crucial part that ticks at billions of cycles per second, controlling the speed at which instructions are executed. Together, these components make the modern computer the powerful tool it is today. Let's go back in time for a moment. Once computers were no longer room-sized machines, engineers worked to make their internal components smaller, faster, and more efficient. One of the key innovations was the transistor, a tiny electronic switch. By 1958, engineers had figured out how to put multiple transistors onto a single chip, creating what's called an integrated circuit, or IC. This paved the way for Moore's law, the prediction that the number of transistors on a chip would double roughly every 2 years. And for decades, that prediction held true. More transistors meant more processing power, without increasing size or cost. In 1971, Intel released the 4004, the world's first microprocessor on a single chip, with 2,300 transistors. It could execute instructions, perform logic operations, and run programs, all on something small enough to fit on your fingertip. By 2012, that number had exploded into the billions, with processors containing multiple cores, meaning they could run multiple tasks at the same time. Thanks to these advances, we now have incredibly powerful computers in our pockets and on our wrists. Now let's bring things back to programming, specifically scripting languages. Unlike compiled languages like C or Java, where code is translated into machine instructions ahead of time, scripting languages are interpreted. That means your code is read and executed line by another program called an interpreter. This makes scripting great for rapid development and cross-platform compatibility, because as long as the interpreter is installed, you can run your script on any machine. In the late 1980s, Guido van Rossum began developing a new scripting language. He based it on an earlier language called ABC, and he called his new creation Python, not after the snake, but after the British comedy group Monty Python. Guido's goals were clear. He wanted a language that was simple, readable, and powerful. And Python delivered on all of those. Over time, it grew into one of the most widely used scripting languages in the world, thanks to its clean syntax and versatility. From web development and automation to data science and artificial intelligence, Python is everywhere. Python has gone through several major versions, each introducing new features and improvements. Python 1.0 was released in 1994 and introduced support for functional programming. IDEs borrowed from languages like Lisp. Python 2.0, released in 2000, brought in garbage collection, a way to automatically manage memory, along with many other enhancements. But Python 3.0, launched in 2008, was a big shift. It fixed several design issues from earlier versions, but in doing so, it broke backward compatibility, meaning code written in Python 2 didn't automatically work in Python 3. This created a long transition period, and Python 2.7 remained in use for years. It officially reached end of life in 2020, and since then, Python 3 has become the standard. Today, Python is completely open source, meaning the community helps shape its development. It has a massive user base, an ever-growing collection of third-party libraries, and is one of the most accessible languages for beginners. In fact, as of January 2023, Python was ranked the most popular programming language in the world, according to the TIOB index, with over 16% of developers choosing it as their primary language. Before we close, let's talk about something that's at the heart of every good programmer's mindset: precision. Programming isn't just about writing code that works. It's about writing code that works correctly, down to the last detail. That includes white space, those spaces, tabs, and new lines that might seem invisible, but can completely change how your code behaves or how your output is interpreted. In programming challenges or automated grading systems, even one extra space can cause your program to fail. Why? Because programming is all about exactness. Think of the difference between equals and equals equals. One assigns a value. The other checks for equality. Or consider an off-by-one error, like looping with I less than or equal to 10 instead of I less than 10. The logic of your code has to be airtight. This is why learning to match output precisely, including formatting, is a valuable skill. It teaches attention to detail, patience, and the discipline to refine your work until it's exactly right. These habits lead to better code, fewer bugs, and faster development. Let's end with a quick summary of everything we've covered. Programming is the art of writing instructions that a computer can follow, from input to processing to output. Python is a high-level language that makes it easy to get started, but also powerful enough for professionals. We've explored how to run code, handle input and output, debug errors, and understand how computers work at a fundamental level. We've also seen how Python has grown over time to become one of the world's most popular languages. If there's one message I want to leave you with, it's this: programming is about thinking clearly and precisely. And like any craft, it gets easier the more you practice. So stick with it, experiment often, and enjoy the journey. Thanks for watching. Let me know in the comments if there are other topics you would like me to talk about. If you enjoyed this video, please like, share, and subscribe for more content on software engineering and technology. See you next time.